In the middle of the South China Sea, on a small patch of water northwest of Hong Kong Island, engineers once stood on a boat and made a decision that sounded closer to science fiction than civil engineering. They would build one of the busiest airports in the world, not on land, not near the shore, but directly on top of the ocean. No ground, no foundation, no island, just water, wind, and a vision that most people would have called impossible. Hong Kong in the 1980s was choking. Kai Tak Airport, wedged between skyscrapers and mountains in the heart of Kowloon, had become one of the most dangerous and congested airports on the planet. Pilots had to execute a sharp 47-degree turn just before landing, dropping low over rooftops while passengers could almost look into apartment windows. The runway ended at the edge of the harbor. One mistake meant the bay. The city had outgrown its airport completely, and there was simply no land left to expand. So the question was not whether Hong Kong needed a new airport. Everyone agreed on that. The question was where. And in a city surrounded by water, steep hills, and some of the most densely packed urban land in the world, the answer was brutal in its logic. If there is no land, you build the land yourself. The site chosen was Chek Lap Kok, a small island off the northern coast of Lantau. It was mostly uninhabited, relatively shallow in the surrounding waters, and far enough from the urban core to reduce noise impact. But the island itself was far too small for a full international airport. The solution was to level it almost entirely, use that material as part of the fill, and then reclaim a massive platform from the surrounding seabed. The finished island would be roughly 3,000 acres, big enough for 2 runways, a terminal the size of a small city, and all the infrastructure of a modern aviation hub. What made this project different from other reclamation projects around the world was not just its size. It was the speed, the precision, and the stakes. Hong Kong was not building a backup facility or a regional hub. It was replacing its only major airport, the one handling millions of passengers and billions of dollars in cargo every year, while that airport was still fully operational. The replacement had to be ready on a fixed deadline. The old airport would close on a Saturday night. The new one had to open Sunday morning. There was no margin for delay and no second chance. That pressure shaped every decision that followed. Before a single runway could be drawn on paper, 2 mountains had to disappear. Chek Lap Kok Island was not flat. It had rocky hills rising more than 100 meters above sea level, covered in vegetation and shaped by millions of years of geology. A neighboring islet, Lam Chau, sat just offshore. Both had to go. Not partially, not reshaped. Completely leveled down to just a few meters above sea level. Their material could be used as part of the fill for the new platform. It was demolition on a geological scale. Drilling rigs and blasting teams moved onto the islands and began breaking apart the rock systematically. Controlled explosions fractured the hillsides. Excavators tore into the slopes. Dump trucks ran in continuous loops, carrying broken rock to designated fill zones. The noise was constant. The dust was visible from across the water. Day after day, the hills shrank. What had been a natural island landscape slowly became a flat, raw construction platform, stripped down to bedrock and waiting for the next phase. But leveling the islands was only half the problem. The airport needed far more land than Chek Lap Kok could provide even after grading. The surrounding seabed had to be reclaimed, and that meant understanding what lay beneath the water before dumping millions of tons of material on top of it. Survey vessels mapped the bay floor in detail. The seabed was not uniform. Some areas had solid rock close to the surface. Others had deep layers of soft marine mud, the same kind of unstable material that causes reclaimed land to sink unevenly over time. Engineers had to decide where to dredge the mud away entirely, where to treat it in place, and where to install vertical drain systems. These systems would allow trapped water to escape as the fill compressed the ground below. Getting that decision wrong would mean a runway that cracked, a terminal floor that tilted, or utility systems that sheared apart. Different sections of the island would settle at different rates. For an airport that had to be operational from day one, Uneven settlement was not an inconvenience. It was a catastrophe. Once the ground preparation was complete, the reclamation itself began in earnest. Barges arrived in a constant stream, loaded with rock, sand, and fill material sourced from quarries across the region. The material was dumped along the perimeter first, building up the seawall that would contain everything else. Then the interior was filled layer by layer, compacted, tested, and raised again. The outline of the island grew steadily outward across the water. At peak construction, the site was running around the clock. Over 20,000 workers were on the project. The scale was unlike almost anything attempted before in civil engineering, and the island was not even finished yet. The island existed, but it was not stable, not yet. Reclaimed land does not behave like natural ground. When millions of tons of rock and sand are piled on top of a seabed, the material beneath begins to compress. Water trapped inside the soil slowly squeezes out. The ground consolidates under its own weight, and as it does, the surface sinks. This process is called settlement, and on a project the size of Chek Lap Kok, it was not a minor concern. It was one of the central engineering challenges of the entire construction. The problem was not that settlement would happen. Engineers expected it. The problem was making sure it happened evenly, predictably, and fast enough to meet the construction schedule. An airport runway can tolerate almost no variation in surface level. A difference of just a few centimeters across a long stretch of pavement can affect drainage, structural integrity, and the safety of aircraft moving at high speed. If one section of the island settled faster than another, the consequences would ripple through every system built on top of it. To control the process, engineers installed thousands of vertical band drains deep into the seabed before the fill went in. These thin, ribbon-like strips of synthetic material acted as pathways for water, pulling moisture out of the compressed clay layers far faster than nature would allow on its own. The water migrated upward and out, the soil consolidated more quickly, and the settlement that might have taken decades was compressed into months. On top of that, engineers used a technique called surcharging. They deliberately piled extra fill material above the final design level, adding weight to accelerate consolidation. Once the ground had settled sufficiently under that extra load, the surplus material was removed and the surface was brought back to the correct elevation. It was a controlled, calculated way of forcing the island to do in months what it would otherwise take years to complete. Throughout this entire process, a dense network of monitoring instruments tracked what was happening beneath the surface. Settlement plates, piezometers, and survey benchmarks were embedded across the island, feeding continuous data back to engineers. Every reading was compared against the predicted model. When the numbers diverged, the team adjusted. More drains, more surcharge, more time in a specific zone. By the time the island was declared ready for construction, it had already done most of its settling. The ground beneath the runways and terminal was stable, predictable, and engineered to remain that way. What looked like solid land from above was actually the result of an invisible battle fought entirely underground, one that had to be won before a single foundation could be poured. With the island stabilized, the real construction could finally begin, and the first priority was the runways. 2 parallel runways were planned for Chek Lap Kok, stretching nearly 4,000 meters each across the northern and southern edges of the island. At that length, they could handle the largest aircraft in service, fully loaded 747s and the wide-body jets that would define international aviation for decades to come. But building a runway is not simply a matter of laying asphalt across flat ground. It is one of the most demanding paving operations in civil engineering. Tolerances are measured in millimeters, and the consequences of getting it wrong are measured in lives. The foundation work came first. Multiple layers of crushed stone and stabilized subbase material were laid down and compacted in strict sequence. Each layer was tested for density before the next one went on top. The goal was a foundation that could absorb the repeated impact of aircraft landing at high speed without flexing, cracking, or allowing water to penetrate. Below the pavement, a network of drainage channels and pipes was installed to pull rainwater off the surface and away from the structure as quickly as possible. In a city that receives typhoons, standing water on a runway is not a weather nuisance. It is a flight safety emergency. The pavement itself was concrete, chosen over asphalt for its durability and load-bearing capacity under heavy jet traffic. Crews worked in carefully sequenced pours, allowing each section to cure before moving to the next. The surface was ground to an exact smoothness, then marked with precision. Center lines, threshold markings, touchdown zones, edge lighting conduits. Every element had to align with international aviation standards to the letter. Beneath and alongside the runways, a vast web of hidden infrastructure was being installed simultaneously. Electrical conduits for runway lighting, underground fuel hydrant pipelines running to aircraft stands, communication cables linking the airfield to the control tower, drainage mains connecting to pump stations around the island perimeter. None of this was visible from the surface, but all of it was essential. The runway above was only the top layer of a deeply engineered system. The taxiway network came next, connecting both runways to the apron and terminal. Widths, turning radii, and surface grades were all calculated around the specific aircraft types the airport would serve. Apron slabs were poured thick enough to support the static weight of fully loaded wide-body jets sitting at the gate for hours. When the airfield was complete, it looked almost simple from above. 2 long strips of concrete across a flat island. But underneath that surface was the most precisely engineered ground in Hong Kong. An airport on an artificial island is only useful if people can reach it. Chek Lap Kok sat off the northern coast of Lantau, separated from the urban core of Hong Kong by water. There were no roads, no rail lines, no bridges, just open sea between the new airport and the 7 million people it was built to serve. Connecting the island to the city was not a secondary problem to be solved after the airport was finished. It was a parallel engineering challenge of almost equal scale, and it had to be completed on exactly the same deadline. The centerpiece of that connection was the Tsing Ma Bridge. When it opened in 1997, it was the longest suspension bridge in the world, carrying both road and rail traffic. Its main span stretched nearly 1,400 meters between 2 towers, rising over 200 meters above the water. The scale was extraordinary. But what made Tsing Ma genuinely unique was its enclosed lower deck. Hong Kong sits in a typhoon corridor. Winds during major storms can exceed 200 kilometers per hour. A conventional bridge would have to close during severe weather, cutting the airport off from the city at exactly the moments when emergency access matters most. The enclosed lower deck solved that problem. When conditions on the open upper road became dangerous, traffic could be rerouted inside the bridge structure itself, protected from the wind and continuing to move. Tsing Ma was the most visible part of the connection, but it was not the only one. The Kap Shui Mun Bridge carried the road and rail link across the next stretch of water to Lantau. The Ting Kau Bridge handled additional traffic further along the route. Together, these structures formed the Lantau Link, a chain of bridges and viaducts that carried the airport express rail line and a 6-lane highway from the urban core all the way to the terminal entrance. The airport express itself was a feat of a different kind. Designed specifically for the airport route, it connected Hong Kong Station in the heart of the city to the terminal in just 24 minutes. Passengers could check in their luggage and receive boarding passes at the city station before ever reaching the airport, clearing one of the biggest bottlenecks in the passenger experience before it even began. Inside the terminal, the passenger automated people mover linked the main building to the satellite concourse, carrying passengers across a structure so large that walking the full length was not a realistic option. Every connection had been engineered with the same logic as the island itself. Nothing was left to chance. On the night of July 5, 1998, Kai Tak Airport handled its last flight. After decades of white-knuckle approaches over Kowloon rooftops, after millions of passengers and countless near misses on that harbor edge runway, the old airport went dark. Ground crews shut down the systems. The lights on the runway were switched off for the last time. and somewhere across the water, a new island waited for morning. What happened in the hours between was one of the most complex logistical operations in aviation history. Hundreds of aircraft had to be repositioned. Ground equipment was loaded onto convoys and driven across the Lantau link. Baggage systems were activated. Control tower communications were transferred. Check-in counters were powered up. Fuel systems were pressurized. Every department of a fully functioning international airport had to be moved, tested, and declared operational before the first departure was scheduled at the new facility. The window was roughly 14 hours. There was no rehearsal. If something failed, there was no fallback. The opening did not go perfectly. In the first days of operation, the cargo handling system struggled under real-world load in ways that testing had not fully revealed. Baggage delays frustrated passengers. Some logistics systems needed rapid adjustment. The problems were real and widely reported, and they were a reminder that no amount of engineering preparation can fully simulate the chaos of actual operations at scale. But the runways worked. The terminal handled passengers. The bridges carried traffic. The airport express ran on schedule. The core of what had been built, the island, the pavement, the structure, the connections, performed exactly as designed. Within weeks, the operational issues were resolved, and Chek Lap Kok settled into its role as one of the busiest and most efficient airports in the world. The numbers behind the project remain staggering. Roughly 350 million cubic meters of material were used in the reclamation. The terminal building, designed by British architect Norman Foster, was at the time of opening the largest covered structure on Earth. The entire infrastructure program, including the bridges, rail line, and highway, cost over $20 billion and was completed in just 6 years. What Hong Kong built at Chek Lap Kok was not just an airport. It was proof that a city with no room left to grow could still find a way to grow. That an island could be engineered from open water on a deadline. That the impossible, given enough precision and enough will, has a way of becoming the blueprint for what comes next.